Greetings! Welcome to the first part of Unit 2, and in this part we're going to discuss the difference between vectors and scalars. So, vectors and scalars both come up in physics. Vectors are something that have both a magnitude, magnitude is a fancy word for a size, and a direction, whereas a scalar only has a magnitude. A good example of a scalar that you encounter in your everyday life would be speed. Okay? If I ask you how fast you're going, you would look at the speedometer on your car and you would tell me maybe like 45 miles per hour. That is telling me your speed. Nowhere in there do you express what direction you're traveling in. Right? If, however, let's say you were following a car and talking to the cops, and you tell them that you were on I-70 traveling behind a vehicle that was going 70 miles per hour east. Well, now not only have you given how fast you're going, but you've given the direction. So instead of expressing the speed of your car, you have now expressed the velocity of your car. Other things that you will encounter that are scalars. Time is a scalar. Mass is a scalar. When we get to it, energy is a scalar. Other things that you will encounter throughout this course that are vectors. Position, displacement, acceleration, force, and momentum. These lists are not exhaustive. We will encounter other things that are either scalars or vectors that are not on this list. Okay, just kind of get you going and thinking. Remember, vectors have a direction associated with them. Scalars do not. Okay. Because direction matters, we have to think about the directions, and we have to think about how to express them. So the first thing I want you to think about is relative motion. So right now, everything is moving. And you may be thinking, no, Dr. Murphy, I am sitting on my couch in my living room, and I'm as still as I can be while listening to this scintillating lecture. Okay, so I'm dreaming a little bit. And I would argue, okay, your reference frame is your couch in your house. My reference frame is the sun, and we are on a planet that is spinning on its axis and orbiting the sun. Therefore, we are moving. And it's all about how we choose to describe our motion, how we choose to think about it. Okay. So now, as an illustration, you're traveling in a car moving south at 50 miles per hour. What is your speed relative to a second car traveling south at 50 miles per hour? Well, if car 1 is moving, I'm going to let this direction be south for the moment, moving south at 50 miles per hour, and the car you're in is also moving south at 50 miles per hour, then this distance between them is fixed. And so relative to that other car, your speed is 0 miles per hour. The distance between you is fixed. However, if you're behind a car that is moving 25 miles per hour south, just like you, then that distance is no longer fixed. It's going to close. Is it going to close at 50 miles per hour? No, it'll close at 25 miles per hour. Oh, I can't write here. Okay, what if you're traveling south, and since I let this be south at 50 miles per hour, and the other car is coming at you in the opposite direction, 50 miles per hour? Right? Now your relative speed is definitely not 0, and it's definitely not 50 because you're both moving towards each other. So your relative speed is going to be 100 miles per hour. Similarly, if the car is traveling north at 25 miles per hour, the relative speed would be 75 miles per hour. Okay. What about relative to the stationary car on the side of the road? Okay. Relative to that stationary car, this is where the 50 miles per hour comes in. Okay. All depends on how you look at it. Which means we need to come up with a good way of being able to communicate what's going on in a problem. And the way that we do that is by putting in a coordinate system. This defines positive and negative directions, and this is one of the things that always frustrates students, is there's no right way. There may be ways that make your life easier, but there's no right way, and you're free to do things in a variety of ways. So here I've written, you're free to put 0 anywhere. So what are we talking about? The most basic coordinate system is just a number line. And usually you think about a number line with 0 in the middle and positive numbers going to the right and negative numbers going to the left. But is there any reason that I couldn't define a number line with, say, 0 here and negative going to the right? No, I could do it that way. I have to be self-consistent with the choice that I've made when I work the problem. But as long as I'm self-consistent, it will work out correctly. I may also have to interpret my answer within my coordinate system. But again, as long as I'm self-consistent, I'll be okay and I'll get the correct answer. Okay. Number lines are the most basic coordinate system. Okay. More complex coordinate system is one that would have 2 axes. So maybe one where positive is to the right and another one where positive is up. This one is very traditionally used in physics, where positive x is to the right and positive y is upward. There are times, however, in this class when we're going to want to do this and rotate the whole thing sideways. There may also be times when we want to do this. Make positive x go to the left and maybe positive y go up. All possibilities. Again, as long as you're self-consistent and do things in the coordinate system you've defined as you've defined it, you can get the correct answer. That concludes part 1. On part 2, we're going to jump into the position vector.